Today we are going to discuss the Hess's law. So Hess's law states that the enthalpy change in a chemical reaction is same whether the reaction takes place in a single step or in the several steps. So enthalpy is a state function, and therefore enthalpy change in a chemical reaction in going from some initial state to final state is independent of the path followed by the reaction. Thus, in going from particular set of reactant to the particular set of product, the change in enthalpy is the same whether the reaction takes place in one step or in many steps. So this principle is the Hess's laws principle, and it was given by Hess's G.H. Hess in the year 1840. Mathematically, we represent it as sigma del H cycle is equal to 0. Suppose a reactant A changes into the product B in one step and enthalpy change in this step is del H. Now suppose this change takes place in 3 steps involving from A to C, C to D and D to B finally, like as shown in the figure. So directly the reactant can be converted into products or it can take the several steps. But the enthalpy changes that are involved in these steps are equal to the total enthalpy change. If del H1, del H2 and del H3 enthalpy changes in these steps, then according to Hess's law, del H is equal to del H1 plus H2 plus del H3. We have example here that is of combustion of carbon to carbon dioxide evolves 393.5 kilojoule of energy. So carbon plus oxygen gives us CO2, that is equal to del H naught is equal to minus 393.5 kilojoule of energy. This reaction takes place in 2 steps. First of all, carbon reacts with half oxygen to give carbon monoxide, and in the second step carbon monoxide plus half oxygen gives us carbon dioxide. So the net reaction will be carbon plus C plus O2 gives us CO2. So del H1 plus H2 we will get the minus 393.51 kilojoule of liberation of energy. So thus the enthalpy change in a chemical reaction is independent of the path followed. Like we can see in this energy cycle diagram, that carbon plus oxygen gives us CO2, and in the second diagram, first of all carbon plus half oxygen gives us carbon monoxide plus half oxygen, and then we will have the carbon dioxide. So 2-step process. So the energy will be distributed into 2 steps, and when we add them up we will get the total enthalpy change. There are many compounds which cannot be prepared directly from the elements. Some of these are like we have CCl4. Some elements do not burn completely due to the formation of protective covering on the surface, such as aluminium and boron. Thus enthalpies of formation of CCl4, Al2O3, B2O3 cannot be determined directly by the calorimeter. Hess's law is particularly useful for determining these enthalpies. Now we have another example in which there are 4 different equations given. So enthalpy of formation of methane cannot be measured directly by the application of Hess's law. It can be measured indirectly from the enthalpies of combustion for CH4, H2 and C, which is carbon. So to obtain del H naught for the required reaction, we must know how combined equations produce the reaction and add the corresponding del H values. This can be done by focusing on the reactants and products. The reactants are carbon 2H2 and the product is CH4. How can we obtain the correct equation? So they are saying that reaction 3 has carbon as a reactant which is needed in the required equation. Thus equation 3 will be used. Equation 2 has H2 as a reactant but required equation needs 2H2. Thus equation 2 will be used after multiplying by 2. Equation 1 has CH4 as reactant but is needed as a product in the required equation. Thus, equation reaction must be reversed and the sign of del H naught is changed accordingly. Adding the equation, deleting the species that occur on both species, we get both sides. We get carbon dioxide plus 2H2O gives us CH4 plus 2O2. Then 2H2 plus O2 gives us 2H2O. Carbon plus oxygen gives us CO2, and carbon plus 2H2 gives us CH4. So the enthalpy change will be minus 74.6 kilojoule per mole. So in the first equation they reversed the equation, so they also reversed the sign. In the second one, half oxygen is were using, but in this one they are using O2 molecule, and in the product we got 2 moles of water, and the third one remains the same. In the fourth one we have the enthalpy change, that is minus 74.6. Now we have the enthalpies of reactions from enthalpies of formation. It is often convenient to calculate the del H naught values for a reaction from values of the standard enthalpies of formation. Del H formation of the reactant product. For a given reaction, del H naught is equal to sigma coefficient del H F naught product and sigma coefficient del H F naught reactant. So we have to minus the coefficients of products with the coefficients of reactants. Elements in their standard states are not included in this calculation, and the del HF naught for an element in its standard state is 0. When balanced equation for reaction is multiplied by integer, the value of del H naught for that reaction should be multiplied by the same integer. Like we have the example in which 2C8H18 plus 225O2 gives us 16CO2 plus 18H2O. So we are multiplying the coefficient of carbon dioxide and adding it into the coefficient of water. So first we have to add these two coefficients for the reactants and the products, and then we will subtract the coefficient of products with the coefficients of reactants, and in this way we got minus 1.09 into 10 raised to power kilojoule. And in the next example they are also doing the same. And for the calculation of combustion we are again using the same formula, just finding the coefficients of products and then subtracting them with the coefficients of reactants. Now we have next important topic, that is Born-Haber cycle. This is a special application of Hess's law to binary ionic compounds. It helps us to calculate the lattice energies of binary ionic compounds. The change in energy that takes place when separated gaseous ions are packed together to form 1 mole of an ionic solid is called lattice energy. So it is basically the change in energy, and takes place when separated gaseous ions are packed together to form 1 mole of ionic solid. So when the ions combine together, so they form a mole of ionic solid, and the energy change that happens is basically the lattice energy. M positive plus X negative gives us Mx solid. Lattice energy cannot be determined directly, however it can be determined indirectly by means of Born-Haber cycles. Born-Haber cycle basically deals with the ionic compounds and calculate the lattice energies. It's an application of Hess's law. Consider the case of NaCl. Its standard enthalpy of formation is minus 411 kilojoule per mole. The formation reaction can be considered as taking place in several steps. So what is the step 1? It is step 1 sublimation of solid sodium. The energy of sublimation for sodium is 108 kilojoule per mole. Sodium in the form of solid converts into gaseous state, and because it's melting, so it's absorbing the energy, and 108 kilojoule per mole of energy is absorbed. After that sodium will ionize into gaseous ion. So Na gives us Na positive plus 1 electron, and again plus 496 kilojoule of energy is absorbed. Second, we have the case of chlorine. So this, first of all, the dissociation of chlorine happens, and chlorine will break into 1/2 mole of Cl2. So the 1/2 mole of Cl2 will be broken into chlorine gas. So this energy required to break the bond is 1 to 1 kilojoule per mole, and the enthalpy of atomization. So 1/2 Cl2 gives us Cl gas, and enthalpy of atomization will be positive 121 kilojoule per mole. After all these steps, so these steps were endothermic, and now we have the exothermic step. Step 4. In the step 4, the chlorine will gain an electron and give us the ion, like we made the sodium ion, so we have to make a chlorine ion as well. So it will require minus 349 kilojoule per mole energy, and this energy will be liberated. Formation of solid sodium chloride from the gaseous sodium and chlorine. This corresponds to latest energy for NaCl, which is to be calculated. So in the step 5, we have to calculate the latest energy. Na positive plus Cl negative gives us NaCl. So this is the 5-step process. In the first step, we got sodium in the form of gas, and then this sodium will lose an electron and convert into the sodium ion. Then we have the Cl2 that will 1/2 Cl2 will convert it into the Cl atom, and in the next step that Cl will gain the electron, and in the 5th step they both ions combine to give NaCl. So we have to add all these enthalpies, like first enthalpy of sublimation, then enthalpy of ionization energy, then atomization, then electron affinity, and the last we have enthalpy of lattice. So we have enthalpy of formation given in the question, that is minus 411 kilojoule. So we have to add up all these, and we get minus 787 kilojoule per mole of enthalpy of lattice for the sodium. So they have written all the steps here, and the net reaction will be sodium plus half Cl2 gives us NaCl. And this is the Born-Haber cycle. So we have the NaCl and minus 411 kilojoule del H naught formation. Then we have the del H naught sublimation. Then we have next the ionization energy, then the atomization, and after that electron affinity, and in the last we have the lattice enthalpy change, lattice energy. So this is the Born-Haber cycle. First of all, sodium solid is converted into the gaseous state, sublimation step, and after that into the in the cation, and after that there is a chlorine, and chlorine will be converted into chlorine gas. Half chlorine will be converted into chlorine gas, and now this chlorine will gain the electron of the sodium, and we got Na positive and Cl minus, and at the end we got NaCl. So this is the overall cycle. Now, what are some factors that affect the lattice energies? The magnitude of the lattice energy is influenced by the charge density of the ion. The charge density is defined as the ratio of ionic charge to the ionic radius. Ionic charge. So, magnitude of ionic charge is important in determining the lattice energy. As the magnitude of ionic charge is more higher, the lattice energy is also higher. The reason is that the higher charges have strong electrostatic attractions and they release higher energy when they come together to form an ionic lattice. For example, MgO has higher lattice than the NaCl. This is because Mg plus 2 and O minus 2 ions have large magnitude as compared to Na positive and Cl negative. Ionic radius also contributes that when the radius is high, the lattice energy decreases. This is due to the larger ion size and electron-electron repulsion, and there is a greater distances, so weaker electrostatic attraction exists, and larger ion needs less energy to separate them, so there will be the lower lattice energies. For example, lithium fluoride and potassium fluoride, when we compare them, they have the same ionic charge but different ionic radius. Lithium is small and potassium is large. So lithium fluoride has high electrostatic attraction and as compared to potassium fluoride, so lithium has higher lattice energy than potassium fluoride. Now we have role of hydration in the dissolving process. The energy change of solution formation depends on three types of interaction: solute-solute, solvent-solvent, and solute-solvent. So when a solution is formed, the interaction between solute particles are broken. At the same time, the solvent molecules also move apart to accommodate the solute particles. Because it takes easy to break the interaction, therefore both processes are endothermic. At the same time, interaction between solute and solvent hydration occurs. Solvent molecules surround the solute particles on all sides. Energy is released in these interactions, so it's an exothermic process. The strength of these two types of interaction determines whether the dissolution process is endothermic or exothermic. So there are three types: solute, solute, and solvent, solvent. So to break the interaction, we have endothermic process, and in order to make a bond, when the hydration occurs, we have the exothermic reactions. Therefore, when a solute dissolves in water, the attractive force of solute particles must be overcome to break the solute particles out of the solid lattice. Strong force must bind these separate solute particles to water molecules. Therefore, the heat of solution measures the net flow of energy that occurs when a substance is dissolved. The energy required to break the solute particles is equal to the lattice energy of the solute. On the other hand, the energy released when solute particles bind to water molecules in solution. So when the solute particles need to break, we have to give the energy, and when the released when the solute particles bind to water molecules, and it is equal to the enthalpy of hydration. For other solvent, the energy is called the heat of dissolution. The enthalpy of solution includes both the energy required to push the solvent molecules apart and energy released when they surround the solvate particles. So the enthalpy of solution is the difference of del H lattice and del H hydration. So del H solution is equal to del H lattice minus del H hydration. When del H solution is very large, solute is unlikely to soluble, but if del H is moderately positive, then solute dissolve. For example, when ammonium nitrate dissolves in water, so it has an energy of 25.7 that is absorbed and the flask become cold. This is because crystal binds NH4 positive and NO3 negative ions more tightly than the solution. NH4NO3 plus H2O gives us NH4 positive plus NO3 negative. On the other hand, if the solvent binds solute particles more tightly than the crystals, energy is released, and it's an exothermic process. For example, when NaOH dissolves in water, 44 kilojoule per mole energy is released and the flask becomes hot. So energy is released when the solvent binds the solute more tightly, and energy is absorbed when the solvent binds the solute loosely, and the crystal interaction is more strong. So energy is always absorbed and energy is always released when the solute binds the solvent when the solvent binds the solute. The solution process can be endothermic or exothermic depending upon the latest energy for the solute and heat of hydration. Like we have for the CCl2 it's minus 83.0, and for the MgSO4 we have minus 91.2 kilojoule per mole of heat of solution. Energy cycle involving enthalpy of solution, latest energy, and enthalpy of hydration. So it's also a cycle, and we have the del H solution, del H hydration, and del H reverse lattice. So Mg positive X negative is M positive and M positive and X negative. It's a for the hydration, and then for the solution Mx is converting into M positive and X negative. So according to Hayes' law, del H reverse lattice plus del H hydration. So if the del H is lattice, then we have to subtract the del H of hydration. If it's reverse lattice, then we are adding the del H hydration into reverse lattice. Del H reverse lattice. Del H hydration determined by adding the del H hydration of both cations and anions. Note that del H reverse lattice has the same magnitude as del H lattice, but it has an opposite sign. Now, what are the factors that affect the enthalpy of hydration? So it is also depending on two factors: ionic charge and ionic radius. Ionic charge affects if the ionic charge affects the electrostatic interaction. Ions with a high charge exert stronger forces on water molecules to ion dipole interaction, resulting in high enthalpy. So higher the ionic charge, so the higher the enthalpy of hydration. Therefore, ionic charge increases, the hydration enthalpy also increases. The hydration process becomes exothermic. For example, the hydration enthalpy of MgO is more exothermic than that of NaCl. These compounds are ionic compounds and consist of MgO and NaCl ions. Both MgO have greater charge and so hydration energy is more. Ionic radius affects the size of ion also affects the enthalpy of hydration. Smaller ions have high energy density, exerts a stronger attraction on water molecules. Therefore, more energy is released when they hydrate. Enthalpy of hydration becomes exothermic. On the other hand, larger ions spread out the charge distribution, exert a weak attractive force on water molecules, thus less energy is released. For example, the hydration energy of MgSO4 is greater than that of CSO4. Sulfate ions are common in these compounds. Their hydration enthalpy difference must be due to the magnesium and calcium ions. Both Mg and calcium belongs to group 2 of the periodic table. Mg in the group below calcium, so Mg2 plus ion is smaller than the Ca2 plus ion. Thus, the attraction of water molecules Mg2 plus ions is stronger than that of calcium. As a result, the enthalpy of MgSO4 is more exothermic than that of CSO4. So MgSO4 has higher hydration enthalpy as compared to CaSO4 because of the ionic radius. So smaller ions have high charge density and their hydration energy is more. Factor affecting electron affinity: nuclear charge, atomic size, and shielding effect. Entropy. Entropy is basically the randomness of a system, the degree of disorder and the randomness. Its symbol is S. As the system moves from a more ordered state to a less ordered state, the entropy of the system tends to increase. Melting ice gives a great example. In ice, the individual molecules are fixed in ordered arrangement. As the ice melts, its energy of molecules increases, they gain more freedom of movement and they become disordered. Entropy of the system increases. On the other hand, when water vapors condenses into liquid, the molecules become more ordered and the entropy is getting decreased. If the entropy of the system increases, it is represented by the positive change, and if it's decreasing, then it is a negative change. And in general, when the temperature of a system increases, system entropy also increases, and del S is greater than 0. As the temperature decreases, del H is less than 0. So entropy is basically the randomness, and is getting away from the order. And if the entropy is high, it's a positive value, it's in the positive value. If it's a low, then it's in the negative value. So for the chemical reaction, like del S naught is equal to del S naught products minus del S naught reactants. A plus 2B gives us C. So for the A we have 40 kilojoule per mole, for B 50 kilojoule per mole, for C 100 kilojoule per mole. So we are subtracting it, and we are getting minus 40 kilojoule per mole of entropy change. So the number of gaseous molecules in chemical reaction increases, the entropy also increases. Now we have the last topic for this chapter, which is Gibbs free energy. Gibbs free energy is the measure of amount of usable energy of a system at constant temperature and pressure. It is defined as the enthalpy of a system minus the products of its temperature and entropy. Enthalpy minus temperature and entropy. Gibbs free energy is also known as available energy. So basically the usable amount of energy, and the temperature and pressure will be constant. It is denoted by symbol G after its name discovered American scientist Josiah Willard Gibbs in 1876. G is equal to H minus Ts. G is Gibbs free energy, H is enthalpy, and S is entropy. So Gibbs free energy is a state function, it doesn't depend on the path followed. So change will be del G naught is equal to del H naught minus del Ts. When the reaction is carried out in constant temperature, del T will be 0. So the Gibbs free energy will become del H naught minus del S naught. This equation is called Gibbs-Helmholtz equation. Del G naught is particularly useful in determining the spontaneity and equilibrium state of a reaction. The sign and magnitude of del G naught indicate whether the process is spontaneous, and it has three possibilities. If del G naught is less than 0 and negative, so the reaction is spontaneous and it's in the forward direction. This also means that energy released will be exothermic and tends to move to a lower energy state. If del G naught is positive, so the reaction is non-spontaneous, in the forward direction, it requires energy. So it's an endothermic reaction. If del G naught is 0, so the reaction is in the equilibrium. So it's also important for studying the phase transitions, like from solid to liquid, liquid to solid, solid to gas. Like we have the example of melting of ice. So H2O solid is converting into H2O liquid. At the melting point, del G naught is equal to 0, so the solid and liquid phases are in equilibrium. Below the melting point, del G naught is negative, indicating that solid phase is more ordered. Instead, above the melting point, del G naught is positive, indicating that liquid phase is more disordered. So below the melting point, so it will be solid state and it is ordered, and above the melting point is a positive and liquid phase is more disordered. Enthalpy and calorie contents of food. The amount of energy in a food or drink is measured in calories. Calories in food refer to the amount of energy stored in food which is released through metabolic processes in body. The enthalpy change associated with these processes correspond to amount of energy released or absorbed during the process of digestion and metabolism. So calories is basically the amount of energy we are taking in the food, and the energy content of food is measured in kilocalories and just in calories. 1 kilocalorie is approximately equivalent to 4.184 kilojoules. This conversion factor relates the energy released during a chemical reaction to the calorie content of the food. So basically this is energy that is released through the metabolic processes in our body. Thanks for listening.